Um, okay, just a short remark at the beginning. Some of your colleagues, I'm not sure if anyone is here, asked me if they didn't finish for this week, if they can present the SSL assignment, milestone 1, also next week. As I told during the presentations for the assignment, yes, you can. Of course, there will be a penalty, but it's better for you to present the milestone and get some scores and not to work for first and not to get any feedback. So next week we're gonna have in a similar way a list of presentations. So if you haven't presented your assignment, try to have a presentation next week. Otherwise, I don't know. Maybe you should think about the date for the exam. We are in week 8, so close. We're gonna get to the period of exams. So maybe it would be a good idea to talk among yourselves and decide when you want to have the exam. Cool. Otherwise, any other issues? I don't know, questions, problems, something not clear to with SSL. Everything is clear. I think we can continue. So we're going to start a series of lectures with which focus on probabilistic graphical models. And I think that starting from this year, you have also talked about probabilistic graphical models at knowledge representation and reasoning. So we're gonna try to focus on some of the things you didn't discuss at KRR, or to look at some of the models from a different perspective. So I guess starting from this year, or maybe last year, I'm not really sure, this part should be simpler. And actually, I have seen, I don't know if it's related to the pandemic, but last year the grades were a little bit were a bit higher than in previous years. I guess it's also related to the fact that maybe at KRR you also learn some of the models we discussed at SSL. Cool. So in the first part, we're going to talk about the first type of probabilistic graphical models. So graphical models are a way to describe complex probability distributions. And actually, we're going to see is there a way to describe even models. We're going to look at a linear model for regression in order to see how we can model them with a graph. And the first course will be on Bayesian networks, and which are, as we're going to see, directed probabilistic graphical models. And next week, we're going to talk with Costin about undirected graphical models, Markov random fields. And you're going to see how Bayesian networks can relate to undirected graphical models and which are the inference algorithms that we have for this kind of models. So what we want to say here is that any probability distribution can be expressed as a directed acyclic graph. So this is a DAG. We're going to say the DAGs have some important properties. First of all, some of the algorithms that work on graphs have a better complexity, and we're going to use the fact that these are actually DAGs throughout the lecture. So here we have the joint probability, P of A and B and C. And actually what we have here is that C is conditioned by A and B. So you see what actually happens, each variable from the distribution becomes a node in this directed graph. So A, B, and C are nodes. And we're going to have edges for the conditional distributions. So C is conditioned on A and on B. Therefore, we have edges coming from A and from B into C. And then again, this is multiplied with P of A given B. So we have used the product rule here. And then we can express P of A given B as being P of B given A multiplied with P of A. So this is the most complex joint distribution. So here we have a conditioning on all variables. So any distribution, even the most complex ones, can be expressed using DEGs. We don't have cycles when we talk about probability distributions expressed as a directed graph. And actually, we could extend this even for a k variable probability distribution. Even in this case, we would have something like xk, the last one, will be dependent on all the previous ones. So sorry, we're going to have edges like this, up to x1, so this would be xk minus 1, xk minus 2, x1. So we're going to have edges going like this. So xk depends on all the previous ones. Then xk minus 1 depends again on all the previous ones, and so on and so forth. And of course, x2 only depends on x1. So any probability distribution can be expressed as a DEG. And of course, we have use effects. The product rule effect is a joint probability P of x and y. It's P of y given x multiplied with P of x, and it could be the other way around, P of x given y multiplied with P of y. So we have applied recursively the product rule in the previous slides. So now each time we have a distribution, we can get in a very simple fashion the Bayesian network, the DEG. And if we only have the DEG, you should be able very easily to write which is the corresponding distribution. So in this case, just as an example, we have a distribution with 7 random variables. And we see, so we can start with the nodes. So we can start, so one of the algorithms that is pretty important for DEGs is called, can you tell me? It's an algorithm which only works for DEGs.
Topological sort.
Yeah, topological sort. So topological sort. We're using a bit of algorithm. You see, ML is a mix of mathematics, algorithms, and other stuff, programming, of course. So it's a really nice mix of mathematics and computer science. So we start from the topological ordering from the nodes that have no in edges. So P of x1 multiplied with P of x2 multiplied with P of x3. So they are not conditioned on anything because they don't have in edges. And then in the topological order, x4 is conditioned on all the previous 3. x5 is conditioned on x1 and x3. And then we go x6 conditioned on x4. So we take the edges, and x7 is conditioned on x4 and x5. So now we could write a general formula if you want, a general factorization. So here is P of x, where x it's an array, yes. So it's a set of random variables from x1 to xk. So actually now we can write it. You see, it's a product out of P of xk for each k, conditioned by the parents for that random variable k. So each time we're going to have the probability of a random variable conditioned on its parents. And this way, if we have the graph, we can write very simple, which is a corresponding distribution. So actually, Bayesian networks offer a relation between a directed graph and the corresponding distribution over random variables. And we can express this joint distribution defined by the graph as a product over all the nodes in the graph of a conditional distribution for each node conditioned on the variables corresponding to the parent of that node in the DEG that we have as a Bayesian network. And now probably we're going to say, OK, how can we use what we have learned and combine it with Bayesian networks? I think this is a part which is different from KRR. So most models can also be expressed using probabilistic graphical models, and we'll try to see how we can express the polynomial curve fitting, let's say, or Bayesian curve fitting in general, using a Bayesian network. And we're going to use not the maximum likelihood, but actually the Bayesian treatment for regression. So here we have like a polynomial y of x and w. It's a linear polynomial model. But actually, we could have, instead of x of j, we could have any basis function. It could be something like phi j of x. So it's not only related to polynomial basis function, it could be for any basis function. So this is a regressor function that we learn. So y of x and w, where w are the weights. And now we say, given a set of targets and the weights that we want to learn for the model, we can write the joint distribution. So we have a joint distribution that we want to express. Probability of the weights and the targets. And actually, this is, we write it this way. So it's probability. What do we have here? So we want to apply here the product rule. So this is probability of the targets given the weights, no? So it's probability of the targets given the weights, but actually the probability of the targets given the weights is probability of the targets given y, because the weights are actually influencing y. So it's given probability of the target given the prediction, the functions that we want to compute. Actually here the target is an array. You see it's an array, it's bolded. So it's an array actually of targets. And these targets are independent because the targets T are independent. It's IID data, independent and from the same distribution. We can express as being a product. So P of T given Y, given as a regressor function, it's a product over each Tn, each target given Y. So this is how we got over here. And now, if we know this, we can start depicting the corresponding Bayesian network. So we know that W influences the targets. So we have the random variable W, we have the random variable targets, T1 up to Tn. And actually what happens in order to have like simpler notations, if several nodes have exactly the same set of parents, so you see here several nodes, T1, T2, and so on, have exactly the same set of parents, only node W, then we can use a plate notation. So here we have a plate notation that says, actually we have a set of variables, Tn, each of them have exactly the same parents, in our case W. So this is called a plate, and we have a plate notation in order to express Bayesian network like simpler, in a more compactful way. And here n is the number of elements on this plate, if you want. Cool. And now we're gonna make this model a little bit more complex, because you can say try and actually Bayesian curve fitting was a little bit more complex. And I say yes, it is, of course. So it's Bayesian. So it's Bayesian curve fitting. Therefore, the weights are a distribution, and they are conditioned on something. So they are a Gaussian distribution. And they are conditioned, they have zero mean. So the mean is zero, it doesn't appear, but they are conditioned on the precision. So alpha is the precision. So how much do we allow the weights to vary? And you see now we put alpha over here. So the weights are conditioned by alpha. Therefore, we have an edge from alpha to W. And now you see alpha is not a random variable. It's a hyperparameter. And actually, hyperparameters, because they are not random variables, they are not nodes like they are these. We use this notation as points, if you want, or yeah. So hyperparameters have this special notation, and again here the target doesn't depend only on the weight; it also depends, of course, on the value of the target. So the point xn. And also on the noise that we allow for the model. That we allow for the model, meaning the regressor model. Yeah. So this is sigma power 2, the noise that we allow in the model to capture. And you see, actually, we have added. So now each xn is different for each tn. Therefore, we put it inside the plate. Sigma is the same for all Tn's, therefore it goes outside. So this is like Bayesian curve fitting model, but actually, yeah. So what I say right now, in machine learning models, some of the random variables are set to specific values, and these values are observed. This is why they are set. They are given from the environment. They are given from the problems that we solved. So these are called observed random variables, and in Bayesian networks, these nodes are shadowed or colored. And in our case, the targets in the training set, so Tn, the targets are the observed variable. The other variables which are not observed, they are called latent or hidden variables. And in our case, we have only one, W, the weights of the model. This is a hidden variable that we need to compute. And how do we interpret this? We interpret it having observed the values for the targets, like given a training set with the targets. We can, if we desire to evaluate the posterior distribution of the polynomial coefficients W. So we can compute this posterior distribution of the weights of W. And we can do it because actually the posterior distribution of W, it's actually dependent on what we say here, it's actually dependent on the joint distribution. So actually, this is a joint distribution. So this is the Bayesian network for the joint distribution. And if we condition on the data, so if we are given a training data set, this is actually what we get. And now we can compute the posterior distribution of the weights. And actually, we're going to say, yes, Ryan, we can compute them because we have seen how to compute it in the lecture on linear models for regression. And you can say, if you remember, OK, the posterior distribution was still a Gaussian distribution, but it was like a multivariate Gaussian distribution with a covariance matrix and so on and so forth. It was a little bit more complex to express it. But we can compute it. Like we can compute it using the properties of sum and product rule. Cool. So this is after we are given. So we can compute the posterior distribution after we are given a training set. We can compute the posterior distribution for the weights for the model. And actually, now we should say, but these parameters of the model are not of a real interest for us because actually, so the only reason why we compute the parameters of any model is why we do the training is because afterwards we want to run fit. Yeah, we want to predict. So sorry, why we run fit is because then we want to predict. So the goal is actually to make predictions for new input values. And now let's say if we are given a new input value, x prime, or on the next slide is going to be x hat, like this. We want to find the posterior distribution for the target corresponding to x hat, and on the next slide is going to be t hat. Here is t prime. More difficult to find the t hat symbol. This is not a usual symbol. So, and of course, it's conditioned. T prime or t hat is going to be conditioned on x hat and also on the weights computed given the training data. Therefore, the graphical model for Bayesian regression actually looks like this. So this is a model for the predictive distribution. So the predictive distribution, what we really want to compute, so we want to predict a new target for a new x, so t hat given x hat, and given, of course, the training set. So this is a training set. And these are the hyperparameters of the model. Yeah, so alpha, precision for the weights, and sigma, precision for the noise in the data. These are the hyperparameters of the model. Actually, this is dependent. And here we need to integrate over the joint distribution of the target, the set of targets in the training and the weights. So actually, what we have over here is a joint distribution, is this joint distribution of t hat, t, and w, which can be expressed, and actually is expressed as p of t given w. And this what we have here is probability of t and w, given everything else. So what we have over here is what we had on the previous slides. The joint probability of t and w. And actually, I guess that you can see the joint probability of t and w is this part. So this is what we had on the previous slides. And now we have made it more complex by adding a new random variable t hat and this new hyperparameter if you want. It's a given point, and this is so it's x hat because it's a given point. We know it is not a random variable. We are giving this point, and now we want to compute which are the most probable values for this random variable, and just to be clear, so we are in Bayesian curve fitting. In Bayesian curve fitting, we are not given, so this is not a value, it's a probability distribution, and this is why it's treated as a random variable. So it's actually it's a probability distribution in Bayesian curve fitting. It's not only one value. Cool, so actually this would be the link. So for a number of given models that we know until now, maybe not for all, we can actually compute, we can depict the Bayesian network corresponding to that model. And probably it's simpler to remember the Bayesian network than all the mathematical formulas behind it. And then you can reason about the mathematical formulas and how you get to them. An important fact about Bayesian networks is actually they are usually generative models. So Bayesian networks can be treated as Bayesian models. So if we want to draw samples from a probability distribution depicted as a Bayesian network, so until now the samples have been distributed uniformly, but given let's assume that they are they are not uniformly distributed, so they are not independent. Let's consider we want to sample from a joint distribution, which is more complex. And this joint distribution can be expressed as a DAG, like as a Bayesian network. How we do this? So we start again using these labeled variables. So if you have seen the labeled variables over here, they are actually in correspond. The labels are given by the topological sorting order. So 1, 2, 3, 4, 5. So actually, these labels are actually given by the topological sorting order. So what we say over here in generative models, we say, let's assume we have a DAG where we have the edges, and we can compute using topological sorting a label for the variables such that the lowest ones don't have any in edges, and the ones that have a higher number are actually are at the end of the topological sorting. So actually what we say, we compute a topological sorting. So if you don't know what a topological sorting is a sorting such that the DAG looks like this. So all edges will go, if you want, from left to right. Regardless of how complex the model is, all edges will go from left to right. Therefore, this random variable x1 will only have edges that go from left to right. This will be the last one, x key. And what this algorithm says, this is called ancestor sampling algorithm. It says start from the lowest number, random variable, x1, and for sure x1 doesn't have any in edges. So it's guaranteed that x1 doesn't have any in edges, otherwise this graph wouldn't be a DAG. And because it doesn't have any in edges, it means it isn't conditioned on any other random variables. Therefore, we know its distribution, it's P of x1, conditioned on nothing. And we just sample from this distribution. Like if this is a Gaussian distribution, we know the parameters and we sample from this Gaussian. If it's a uniform distribution, we just sample randomly. If it's discrete, we sample from the discrete and so on. And we'll get 1 point. We'll get x1 star. And now we go through the remaining nodes in order. So x2, x3, and so on. So let's assume that we are at index n. So n goes from 2 to the last one, to k. And now each time we sample P of xn given the parents of node n. And actually the parents of node n are always to the left. Therefore, they have already been sampled. So always for the parents, they have a lower number. Therefore, we know their actual value. So we know all the conditioning for this distribution. Therefore, we can just sample from it. And the last node to sample, of course, would be xk, the last one. And right now we have a sample from x1 up to xk. So we have sample from the complex distributions that we have expressed as a Bayesian network. If we only want a marginal distribution, so let's say we don't want x1 to xk, we only want x2 and x4, we do exactly the same thing. So we sample the full distribution, we discard the rest, and we only keep the required nodes, like only x2 star and x4 star. So actually the algorithm is the same if we want only specific samples. Cool, and now let's see how, so actually we can sample from any Bayesian network, but not always Bayesian networks like are made to be generative models. But when they are generative models, in general, the higher number variables, so the higher number variables, the ones to the right over here, usually they correspond to observations, while the lower number variables, yeah, the one here to the left, they correspond to latent variables. And actually, you can imagine the process is the following. We have to the left latent variables whose role is actually to allow a complex distribution for the observed variables to be represented using simpler conditional distributions. Like when we say simpler conditional distributions, we actually mean distributions from the exponential family, like Gaussian, discrete, or something else. So this is what we mean by simple distributions. Distributions that we have used, like Dirichlet, maybe more complex, but this kind of Gaussian, discrete, Dirichlet. Cool, and so now let's see what, as a simple example, what we have said. So given this very simple Bayesian network, so we said, if we are to take a topological sort over here, this would be the topological sort, x1, x2, x3, x4. And we said that nodes that are to the right, so that have a higher number, correspond to observed variables. So of course, if we take the causal process for generating images, the actual image is what we observe, is the observation. So this is what we have in computer vision datasets. Yeah, we have images with still defects. We have images with animals. We have images with anything you want. Yeah. So actually, most of the time, yeah. So most of the time, what we have observed is this. The other three, they are latent variables. So x1, x2, x3, which are to the left, they have a lower number, lower label. They are hidden or latent variables. So the object, we don't know the object. We actually want to find which is the object in computer vision. The position, the orientation is the same. And now let's see how we can imagine this to be a generative model. So the observed data is the image. And of course, in a recognition task would be the image corresponds to what object. So in a recognition task, we are given the image. We would like to find the object. But let's see in a generative task. So in a generative task, we say that the latent variables have the interpretation of position and the orientation of the object. And now we say that given a particular observed image, our goal would be to find the posterior distribution over objects in which we integrate over all possible positions and orientations. So in a recognition task, actually, if we have the set of objects fixed, like we will have cats and dogs, we would like, in the general case, images from all positions and all orientations. And of course, here you could say triangles. This is not only maybe lighting condition, yeah, and more, maybe that, I don't know, the specific type of cat and dog and so on. Cool. So now let's see how a generative model would work. So the same simple model also can be seen as a generative model. In contrast, so a generative model says that how we generate data, we take a cat and we change the position and orientation of the camera. So we change the distance, we change the angle, and we take as many pictures as we want. So this would be the generative process. So we fix an object, and we change the position and the orientation, and this is how we get as many. This is how we generate images if we would have the mechanism. And actually, this is how we generate data sets now. And we say that not all models are generative models. For example, our polynomial regression models that we have seen is not generative because we don't have any probability distribution associated with X, the input variable. So here, we don't have a probability distribution here. If here we have had a probability distribution, then we could have sampled like fantasy data. So we could make the polynomial regression model generative by adding a probability distribution associated with the input variable X, like it could be a uniform distribution, maybe, and then we could generate synthetic data points from this model. Cool. And so again, as an interpretation, you have seen that hidden variables in the probabilistic model for the image generation, they have like an explanation of a physical interpretation, like we have the image, and the image is generated given the object, given the orientation and the angle. And we say that in machine learning models, we don't really need to have an explicit interpretation. Like we won't have a name. X4 is equal to object, X2 equal to angle, and so on. Many times we add latent variables just to have a more complex model without having any physical or clear explanation from the human point of view, from the real world point of view, if you want. It's only from a mathematical point of view. So sometimes these latent variables are introduced simply in order to build more complex joint distributions from simpler components, like from Gaussian distributions, for example, or from discrete distributions. But in either case, even if they have or they don't have a physical, real-world interpretation, the generative model using the generative model by applying ancestral sampling or similar sampling methods give rise to fantasy data whose probability distribution would be the same as that of the observed data. Of course, it would be the same only if the model were a perfect representation of reality. Like in our case for regression, only if the weights are good enough in order to express the functions that we want to compute. Like if we have computed good enough weights, we can generate synthetic data. If we have bad weights and we don't have a good regressor function, yeah, then we generate bad data. No. It's clear, like in order to generate data, we want the weights to be computed and have good values. So even if we have here a random variable, in order to generate new points Tn, we need to also to know the weights. Yeah. And we need these weights. This is what we say. That the model needs to be a perfect or a very good representation of reality. If it's not a good representation, then we'll have bad fantasy data. Cool. Yeah. And so this was the first part, like an introduction to Bayesian networks. In the second part, we're going to look at how Bayesian networks, which are more complex, they require a very large number of model parameters, which are actually impossible to compute because it's intractable sometimes. And our conclusion would be that we want to have Bayesian networks which have an intermediate power of representation, therefore an intermediate number of weights. So not too few because we'll get a simplistic model, not too many because we'll get a model with an exponential number of parameters that we cannot compute. And we're going to look at two examples of Gaussian, of Bayesian networks. So in the first example, we're going to have Bayesian networks that have discrete variables. Yeah. So discrete variables are an example of discrete distribution. Actually, it's an example from the exponential family. So discrete variable says that we have k possible states, or if you want k categories, which are mutually exclusive. Therefore, most of the times we use a 1 out of k or one hot encoding in order to represent a state. So here x means that actually x3 is equal to 1. Yeah, so x3 is equal to 1, and all the other ones are equal to 0. So here, if you want x, it's in state 3. So actually what we say that we express each observation x as an array of one hot encoding, and the probability, which are the parameters of this distribution. The parameters of this distribution are the probability of being in a state. So probability of xk equal to 1 is the probability of sampling from state k, and it's actually equal to mu k. So usually mu is related to the parameters of a model. If you see mu, it means these are some parameters of a model. If you have a mean, mu is a mean, is a first. Here mu is an array. Therefore, the distribution for a discrete variable probability or discrete variable p of x given mu, so mu is an array, can be expressed as mu k power xk, a product of course of mu k power xk, with the following observations. We are using one hot encoding, therefore only 1 out of xk is equal to 1. So only one xk is equal to 1. All the other ones are equal to 0. And the other observation is that mu should be a probability distribution, so correct should be a correct distribution. Therefore, in order to be a correct distribution, summing up over mu k should be equal to 1. And actually, the interpretation over here would be, let's see which is, if p is in state 3, how would this look like? So if p is in, let's go over here and say, which is a probability of x being equal to 0, 0, 1, 0, 0. So p being in state 3 given mu. The probability would be the following. It would be mu1 power 0 multiplied mu2 power 0, yeah, multiplied mu3 power 1 multiplied mu4 power 0 multiplied mu5 power 0 multiplied mu6 power 0. So you see, we actually get only mu3. So maybe at the beginning it's more difficult to grasp why we have that product, but it's actually a nice way of using kind of an algebraic notation. So p of x being in state 3, it's actually equal to mu3. It's exactly what we have said. Yeah, cool. And because this is a correct distribution, how many values, independent values we have, or different values do we have? How many degrees of freedom, if you want, in order to express x? We have k minus 1 values. So if we have k state, we have k minus 1 values, because the last one would be 1 minus all the previous k minus 1. Cool. And now let's assume we have two discrete variables. If we have two discrete variables, we have two options. The first option would be to have a conditioning between them, like to have a more complex distribution. So this is more complex. So we have a conditioning. Of course, it's more complex. This is simplistic, more simple. Actually, this one is as simple as possible. We have two independent variables. Like it couldn't be any simpler than that. And now let's see how many parameters do we require. So in this situation, we require, so it's p of x1 minus x1 and x2 power mu. They are not independent. If they are not independent, it means that here we actually have a matrix mu kl power x1k x2l. Using a similar notation, this is one hot encoded, and this one is also one hot encoded. So one hot encoded. Both of them are one hot encoded, and this is why it works to have this notation. So we actually have a matrix, and this matrix needs to be a correct distribution. Therefore, we need to compute k power 2, a matrix, minus 1, because the last one will be 1 minus all the others. Cool. So this would be, so here we have k power 2 minus 1 parameters. Another way to reason about it would be to write it, to decompose it, and to say this is p of x2. So to use a Bayesian network, sorry, it's p of x1 multiplied with p of x2 given x1. How many parameters do we have for p of x1? K minus 1 parameters, no? Because it's a discrete distribution. We have k minus 1 with k states. How many parameters do we have to express, do we need in order to express x2 given x1? So to express x2 given x1, actually here we have x2 equal to first state, x2 equal to second state, x1 equal to first state, and so on up to the k state is the last one. So actually here what we say that each row over here, so each row should be a discrete distribution. Therefore, each row over here requires k minus 1 values. Should be a correct distribution. So the last value is actually 1 minus all the other ones. So we have k minus 1 values for each row multiplied. We have k rows over here. So it's k multiplied with k minus 1. So for this one, it's k multiplied with k minus 1. For the last one, it's k minus 1. Therefore, when we sum this up, we have k power 2 minus k plus k minus 1 when we sum up. Therefore, we have k power 2 minus 1 parameters. So we get to the same number, k power 2 minus 1. So these are the two interpretations. So it's either a full matrix, or we have this, we use the product rule in order to get to this combination of two distributions. And now let's see what happens if we have an independent joint distribution. So the second case, if we have independent joint distribution, so it's independent, therefore we can write p of x1 and x2 like being p of x1 multiplied with p of x2, because it's independent. And each one requires k minus 1 parameters, therefore it's 2 multiplied with k minus 1 parameters. And actually, what can you see? You can see that even for only 2 random variables, the number of parameters is actually is a lot more for the more complex case. So if we allow conditioning, so it goes from k power 2, so from 2k to k power 2. And now let's see what happens if we have more random variables. So what happens over here if we have x? So here we have 2 states. What happens for x6? So x6 is conditioned on 2 random variables. If it's conditioned on 2 random variables, we actually need to compute not a matrix like we have here. So it's a matrix. We need to compute a cube of parameters. Therefore, it would be something 2 power in degree plus 1. So it's a cube. It's 2 because 2 is the number of states. Power in degree plus 1. So in degree is 2 plus 1. So we need 2 power 3 parameters. Cool. And now maybe some of you say, "Oh, this is not good." So it's 2 because we have 2 states. But actually, if the number of states is k, and here the in degree, in the worst case, a node could have an in degree actually n. If we have n, it will be k power n. So actually, what happens from a graphical perspective, we can reduce the number of parameters in a graphical model by dropping links in the graph. But if we drop links, we have a simpler class of distributions. Like if we have no links, we have an independent random variable. So we don't have any interesting distribution, maybe. And what we want to do, we want to have graphs that have an intermediate level of connectivity, so intermediate level of edges, to allow us to express general distributions rather than to use a fully factorized, like a fully connected DAG. Cool, and now let's see what happens like if we have so if we have a general joint distribution over n variables, so it means we have a complete DAG. If you can imagine a complete DAG, we will need something like O of k of m minus 1 parameters. It's the discussions that we had over here. So k of, because the in degree for the last node would be n minus 1, so n in degree plus 1 would be n. So if we have n variables, it would be actually k O of k power m minus 1. So actually, it's an exponential number of parameters. We wouldn't be actually able to compute this number of parameters. We wouldn't be able to compute from a computational point of view. So from a computational point of view, k power m, even if k, I don't know, is 3 and m is, I don't know, 20, is too much. Yeah. So even if we only have 10 random variables and 3 states, but most of the times we could have like the states, tens of states or so, even more. Yeah, so we couldn't compute. And second, in order to compute, like imagine we need to compute values for all these hypercube. In order to compute them, we need an infinite amount of data. Because if we don't have an infinite amount of data, many values in this cube, we wouldn't actually have a value for it. We wouldn't be able to know which is a value. So there are two important points. First of all, it's intractable to compute. Second of all, in order to compute it, like to have a powerful model, we need an infinite amount of data. Not infinite, but a very large amount of data that most of the times we don't have. And now we say, let's imagine or let's look on some models like which are not disconnected, like they have some links, but they are not. So this would be general distribution. This is, if you want, a complete DAG of DAG with as many edges as possible. And now let's look at this is called a Markov chain, first order Markov chain. Markov chain says that all the nodes are connected, but we only have one edge going from one to the next. How many parameters do we have here? For this one, we have k minus 1. So for this one, we have k minus 1. And for each of the other ones, we have k multiplied with k minus 1. It's the same rationale that we had over here. So it's this rationale. K minus 1 for the first, and k multiplied with k minus 1 for all the other ones. So actually, it's a good thing that we have reasoned about it on the other slide. And here we have m minus 1 random variables. Therefore, it's m minus 1 multiplied with k minus 1. So you see, this model is tractable. So it's theta of k power 2 multiplied with m parameters. And like this would be a way to reduce the number of parameters. Of course, we could have maybe even more edges, like we could add 2 edges. If we have 2 edges here, it would be k power 3. But still tractable. So this would be a way. This is what we say. We want to reduce the complexity by removing some of the links. That would still allow us to have complex models with dependencies from xk will depend on all the previous ones, but not to have a fully fully edged DAG. Another way to reduce the number of parameters, it's called to share the parameters or to tie the parameters. Like in this case, would be that all conditional distributions, like each time we have a conditional distribution, like x3 depending on x2, x2 depending on x1, would be to share the same parameters, like not to allow them to differ. If they would share the same parameters, actually this term in front would go away. So if we share the number of parameters, it's the same of this term going away. So we will have only k multiplied with k minus 1 parameters. So m minus 1 goes away, and after adding k minus 1, so actually we will have the same number of parameters as for this example. It's only for 2 random variables. Of course, the probability distribution would be less expressive. So if we tie down the number of parameters, the distributions, the model will be less expressive. Cool. Another way, so we could turn a graph over discrete variables into a Bayesian model, also by introducing Dirichlet priors for the parameters. And actually, Dirichlet priors are introduced for discrete. So discrete is also called multinomial variables, because Dirichlet is actually the conjugate prior for discrete variables. So these are called conjugate prior. For the Gaussian distribution, the Gaussian is a conjugate prior. Like when you use the product rule, or when you multiply two probabilities together, when you have conjugate priors, you'll get a simpler formula that can be computed analytically, like using mathematical perspective. So it doesn't require to be approximated. And actually, adding a Dirichlet prior for the previous model would be something like this. So for each node, we add a Dirichlet prior, and now each multinomial is also depending on the Dirichlet random variables that we have. And this one is sampled from a Dirichlet distribution. Dirichlet distribution is used in machine learning a bit. So it's also an exponential family distribution that uses a beta function. So it looks kind of a Gaussian, but it's a little bit more complex. Have you heard at NLP about something related to Dirichlet? Anyone? No one? Did you hear about latent Dirichlet allocation? Did you talk about topic modeling with Professor Trăușan at some point until now? So actually, if you have talked about latent Dirichlet, it's an unsupervised Dirichlet allocation, or LDA. It's an unsupervised technique for computing topics out of a large collection of documents. And actually, this can be expressed as a Bayesian network. So LDA, it's a Bayesian network where we have this. So this is called, it's a latent variable, as you see, and we use a latent distribution of latent Dirichlet distribution over topics. And this is why it's called the latent Dirichlet allocation. Because the topics are multinomial. They are discrete. Each document is a combination of topics. So we have multinomial distribution. And even here, like, we can tie down the parameters. Like, we can use the same Dirichlet distribution instead of having several ones. So we can use the same Dirichlet distribution. Another way of reducing the number of parameters would be to so if we still want to have something like this, so y random variable, let's say the dependent random variable in this case, we would like to depend on all the features. One way of, so if we would express it as a joint probability, it would be y given all the features, and in the worst case would have k power m parameters, so it would be untractable. One way of having like a dependence on all parameters and still being tractable would be to use a linear combination and passing through a nonlinear function. So, and this is actually what neural networks do. So we pass through a nonlinear function like a sigmoid, and what do we pass? We pass a linear combination of the parameters. So in this case, we still have a dependence on all the previous random variables, but we say we want to have a dependence on a nonlinear function given the linear combination. So it's a more restricted form is a conditional distribution, so it's clearly more restricted. It's simpler than this one. But right now, the number of parameters grows linearly, so we have only m plus 1, so it's theta of m parameters instead of having theta of k power m. Yeah, so this would be like the power of the perceptron. Oh, yeah. And actually, the same works for linear models. Like linear models do the same thing, but they don't go through a nonlinear transformation. So it's actually the same thing. But of course, so we still have a combination of all the parameters, but now it's a linear combination. So it's a simpler distribution for sure. Cool. So what we have seen in this part we have seen that if we have very complex Bayesian networks, the number of parameters will become intractable. Therefore, we want to have Bayesian networks which are complex, but not so complex in order to become intractable. So we'd like to have Bayesian networks in the case of discrete random variables. We'd like to have Bayesian networks that have an intermediate level of complexity. Because these are the ones that we can actually use and compute. And actually, the same discussion would be if we have linear Gaussian models. So for a linear Gaussian model, the random variables are continuous. They are actually Gaussian. Actually, not only they are Gaussian, it's a linear Gaussian model, meaning that for each random variable xi, so xi now depends on some parents. So it will depend on some parents. We'll have here some nodes. It will be xi would be conditioned by a mean, and this mean you see it's a mean linear combination given the parents. So summing up over all the parents, we have y of I and j multiplied with xj. So xj is a previous random variable, let's say. And we do this for all the parents. So each node is a Gaussian, but we have a conditioning where the mean is a linear function of the parents. Yeah, it's a simpler conditioning. Of course, we can also work the same if we have multivariate Gaussian. So this is for univariate, this is for multivariate Gaussian. So this is for one node, P of xi. Let's see what happens for the joint distribution. So the joint distribution P of x is actually P of x1 up to the last one, xd. Here we have d, the number of variables. So actually what we say here is that when we compute the logarithm of the joint distribution, we actually see that we get a quadratic function of the components. And this is a way of signaling that actually P of x is a multivariate Gaussian. So the joint distribution for linear Gaussian models, it's actually still a Gaussian distribution, but it's multivariate, like it goes into d dimensions. If it's a Gaussian distribution, we need to compute its mean and covariance. Yeah, if this is a distribution, so it's Gaussian, we need to compute the mean and the covariance in d dimensions, each one. And now let's see what happens for the mean. So first we need to compute the mean. So each variable xi is a random distribution. It's actually a Gaussian distribution. And you see what we write here, we write the mean. So this is the mean for xi plus the standard deviation. So VI is the standard deviation plus the standard deviation multiplied with the variance. Yeah, so this is how we write it. And now we want to compute the expectation for each random variable. So the expectation of xi, and now the mean for the joint distribution would be the expectation for each component. So actually, the expectation, it's simple to compute. We use like a similar technique to ancestral sampling. So we use the topological sorting, and we will get the fact that each time we need to use the expectation of the Gaussian distribution that we depend upon. So we can compute the. So this is the mean. The mean for the joint distribution. We can compute it in a simple way. and it has, of course, D components. And now we need to compute the covariance function. So when you compute the covariance function, of course, the covariance can be computed like expectation of xi multiplied with expectation of xj. And we'll get to the fact that it's actually a matrix, if you want. So covariance of xi and xj, we need to compute a matrix. We need to compute all these weights in order to express it. So again, we have two extreme cases. If we don't have any links in the graph, we'll have de-isolated Gaussian distributions, so independent Gaussian distributions. If they are isolated, actually we won't have any weights over here in these matrices. We only have the biases and the variances. So we have only 2D parameters. And it actually makes sense. Yeah, we have 2 multiplied with D parameters because each Gaussian has a mean and a variance. Yeah, so each one has 2 parameters. We have D Gaussian distributions, they are independent. We have 2D parameters that we want to compute. The second case is when we have a fully connected graph. If it's a fully connected graph, actually this matrix, it's a lower triangular matrix. Therefore, each time each matrix will have D multiplied with D minus 1 divided by 2 elements. And the covariance matrix will have D power 2 elements. So again, we go from theta of D to theta of D power 2 independent parameters, which means that the fully connected model is more complex. We need to compute a larger number of parameters. And again, we say if we go to graphs that have an intermediate level of complexity, so here is not fully connected, this is similar to what we have discussed. So it's a Markov chain, similar to what we have discussed for discrete variables. Actually, we're going to have covariance matrices which are simpler to express. They are kind of in between. Cool. So in the second part of the class, we wanted to show you that even if Bayesian networks are built to model complex distributions, actually we want to have intermediate level of Bayesian networks. So we don't want to have fully connected DAGs because these ones are hard to compute, are difficult to compute, are actually intractable in many cases. We cannot compute them. Therefore, we want to have DAGs with an intermediate level of complexity, like each node to have as in degree a small number of edges, 1, 2, 3, I know, but not n. So this would be the first conclusion that we get to. And now we talk a little bit about why do we use Bayesian networks? Okay, we have been able to build a Bayesian network. We won't discuss algorithm. So a Bayesian network can be built from data. So if you have a data set, you can build the Bayesian networks. There are several algorithms in order to do this. They are not perfect, like they approximate the Bayesian network. It's not perfect to build these Bayesian networks. They have been used a lot, especially in expert systems, like expert systems. For example, in medicine, they are used in medicine. And there is a very nice class on Coursera. Like I think that Daphne Köhler, one of the founders of Coursera, together with Andrew and G, has a very nice class. I think it has 2 classes from Stanford on probabilistic graphical models. She's one of the leading researchers on PGMs. And actually, they provide models for US hospitals and so on. So if you have enough data, you can build these models. Like imagine a graphical model where you have like symptoms and diseases and links between diseases and also treatments and so on. And if you see that somebody is coughing, and so if once you get some symptoms, the probability for each disease changes. And you'll get this automatically as a doctor on your tablet. And then it will ask you, maybe you should ask the patient about if they also have this symptom and so on. Because you know which are the other random variables that might influence the diagnostic as well. Cool. So actually, these models are pretty used in practice. At some point, researchers consider that combining Bayesian models and neural networks would be a way to improve neural networks, and this is called Bayesian neural networks. But in the end, until now, besides some research papers, we don't have anything which is like really useful. But maybe we'll have in the next future. Assume that we have a Bayesian network computed from data, from large data sets, maybe on medical data. And now we'd like to see why do you use Bayesian networks. And we say we use Bayesian networks because we can use simple inference methods. And one of these inference methods uses conditional independence. So conditional independence says, so we know if two random variables are independent, it means that P of A and B, it's P of A multiplied with P of B. Conditional independence said that A could be conditional independent of B given C. So A and B might not be conditional independent, but given C, they become independent. And we express it like this. So A is conditionally independent of B given C. If P of A given B and C, it's actually P of A given C. So if we know C, B does not influence A anymore. And we can write it this way as well. P of A and B given C, it's actually P of A given B and C multiplied with B and C. Yeah, so this is, we apply the product rule. And using the first property, so if we use this definition, by using the definition above, it's actually P of A given C multiplied with P of given C. So you see, if C is given, like if C is observed, we actually have A and B act as though they were independent. So only if C is given, they act as though they are independent. So they become statistically independent only if C is observed, and the notation is A. I don't know how to say that symbol. Perpendicular, if you want, and we read it, A is independent of B given C. Yeah. Cool. And conditional independence properties are very useful for probabilistic models, for machine learning, because they can be used to reason and to simplify the model. Simplifying the model means less computations in order to perform inference and to learn under that model. And actually, they provide a very simple and elegant feature in order to apply inference for any graphical models without performing any mathematical or analytical manipulation. This is called deseparation from directed separation. And we'll go next. So after discussing conditional independence, we go to deseparation. So let's see. Assume we have a Bayesian network. In a Bayesian network, we can only have, if we look at 3 nodes, like at a triangle of nodes, we can only have three types of paths. So the first one is this one, and this is called, this node is called tail to tail. So this is the head, this is the tail. So node C is called tail to tail in this situation. And if none of the variables are observed, so if we don't if we don't know any of the variables, joint probability of A and B and C, we can write it. It's P of C multiplied with A given C multiplied with P of B given C. So P of A and B, in order to find P of A and B, we actually need to apply the sum rule. So actually, it's sum over C out of P of A, B, and C. This is what we say. And this is equal to this sum on the top. And actually, if we don't know C, A and B are not independent. So this is a complex for distribution. It doesn't break up. It's different. It's not equal to P of A multiplied with P of B. It's more complex. So A is not independent of B given anything. So given none. But if C is known, like if C is given, now P of A and B given C, we can write it as a joint divided by P of C, of course, we use Bayes' theorem. And you see, if we divide over here by P of C, actually P of C goes away, and we're going to get that it's P of A given C multiplied with P of B given C. So if we are given C, A and B become conditionally independent given C. Yeah. And actually, in this situation, we say that the inference path from A to B is blocked. Yeah. When A and B become independent given C, it means that if we learn something about A, so if we find out the value of A, nothing will change about B. Cool. And one way of reasoning about this, imagine that C is actually a symptom. C is affected if we know that a patient has fever or not, or is coughing. If we know a patient has fever, and if we know that a patient has fever, then, sorry, no, I don't like it. The latent variable here, like the one on top, this one should be, here we should have flu. So here we have the disease flu because flu gives fever and cough. So what we say, if we know that somebody has a flu and we find out that that person also has a fever, so we find out something about this random variable, this doesn't influence the fact that that person might be coughing. So if we know that it has flu, only the fact that it has flu tells us enough to know if the person should be coughing or not. If we know that it has fever, fever is not related to cough. It's not related on this path. It might be related on a different path, yeah, maybe on some other diseases. Cool. So this would be the way to reason about it. And like this simple graphical interpretation, so here C is called a tail-to-tail node. And if a tail-to-tail node is not observed, therefore the inference path is open. If node C, if this node becomes observed, then the path, the inference path becomes blocked. And this causes A and B to become conditionally independent. The second example is called head-to-tail. So this is a head-to-tail node. It's a second structure that we can get. So for a path from A to B, we could have a node, an intermediate node C, which is head-to-tail. And if C is not observed, the joint distribution here looks like this. It's P of A multiplied with C given A, multiplied with B given C. And now we want to write P of A and B. P of A and B is actually, again, it's in order to get P of A and B, we need to sum up here over all the values of C. P of A does not depend on C, it goes in front, but these two depend on C. And actually, here using the sum rule, the summation rule, we get the fact that it's P of A multiplied with P of B given A. So actually, they are not, again, they are not equal to P of A multiplied with P of B. So they are not independent if nothing is observed. But if C is observed or C is given, then again, we get over here, we divide by P of C. And when we divide by P of C, we're going to get to the fact. So what do we have here? By using, again, base rule, we're going to see that here we have the posterior, sorry, I don't know, I have misclicked. Here we have the posterior distribution of A given C. So actually, A and B now become independent given C. So it's similar to the first case. The interpretation would be if C is not observed, we have an inference path going from A to B, but once C is observed, the inference path is blocked. So if C is head to tail, and it's observed, the path of inference becomes blocked. And this is the last type. This is called a V structure. or a head-to-head node. And for a V structure or for a head-to-head node, we actually have this joint distribution. P of A and B and C is P of A and P of B multiplied with P of B multiplied with P of C given A and B. And again, in order to find P of A and B, what we need to do is to sum up over C. So here we need to apply the sum rule to sum up over C. P of A and P and B don't depend on C, so they go in front, and we actually get it's P of A multiplied with P of B multiplied with sum over C of P of C given A and B. And actually, this sum, this is a correct probability distribution. Therefore, this sum is equal to 1. This is why it goes away, because it's equal to 1. Therefore, in this situation, for a V structure, if C is not observed, A is independent of B. So A becomes independent of B given nothing. So if they are independent given nothing, it means that this inference path now is blocked. So if we don't know C, this path is blocked. Yeah. So for example, what we say right now is that, again, if this is fever, and these are flu, let's say, and this is COVID, if we don't know that somebody has fever, we don't have any link. If somebody has flu, it might also have coronavirus. These are not influenced. So even if we know that somebody has flu, this doesn't mean that somebody wouldn't have also COVID. Cool. So this inference path now is blocked, and we are independent. Now let's see what happens if we observe C. So if we are given C, now P of A and B given C, it becomes like this. And now, of course, if we write, if we want to see what happens with P of A and given C, it's clear that now is not equal to P of A given C multiplied with P of B given C. So it's clear not equal to P of A given C multiplied with P of B given C. It's something more complex. We cannot do anything to get rid of this. So right now, A is not independent of B given C. So if C is observed, this inference path becomes open. So now this path of inference is open, becomes unblocked. And again, using the same reasoning, now if we are given the fact that we have fever, and we also know that we have flu, the probability of having COVID fades away. Yeah. So if we know for sure that we have flu, we find that we have the influenza virus, then we don't have coronavirus. The probability of having coronavirus fades away. It doesn't mean it goes away. It's not equal to 0. We could still have both of them. But they become influenced. The inference path becomes open. So if we have a V structure or a head-to-head structure, so if C is a head-to-head structure, if C is not observed, then the path is blocked and A and B are independent. However, if we are given C, if we condition on C, then we unblock the path and A and B become dependent from an inference point of view. And actually, as a generalization, not only if C is observed, but if C has descendants, if any of these descendants is given, is observed, yeah, then the same is valid. So neither the node in the V structure nor any of these descendants should be observed in order for the nodes to be independent. So in conclusion to conditional independence, if we have tail-to-tail or head-to-tail nodes, then the path is unblocked, and only if the node is not given, C is given, the path become blocked. On the other hand, for V structures, it's the other way around. And if we have an unblocked path, any unblocked path means that the variables, the random variables at the end, they have an influence one to the other. So if we find something about one, the probability for the other will change. And now let's look at the classical example using a V structure from Bishop. So we have our car, and it's a pretty bad car, at least in this example. We have two indicators. so we have indicator for battery. If the battery is flat or not, we have so yeah. We don't. It's not like an indicator. We know if the battery is dead or not. We know if the fuel is empty or not, and we have a gauge reading. Like we have an indicator which requires battery in order to work correctly. And this gauge reading says if the fuel is a fuel gauge, if we have fuel or not. So this is the indicator, the gauge in the car that tells us if we have fuel or not. But in order for this gauge to work correctly, we need to have both fuel and battery. So sometimes we might say that we don't have any fuel, but actually we don't have any battery. Now let's see how this indicator works. If we have battery and fuel, in 80% of the time, the indicator will say that we have fuel, that we have some fuel. So this is not very good. So it's a pretty bad indicator. It should be 0.99 if you want. Cool. Then what happens? Which is a probability is a gauge saying that we have fuel. If we don't have fuel but we have battery, it's 20%. So again, it's pretty bad. Which is a probability is a gauge says we have fuel. If we don't have battery and we have fuel, is still 20%. Which is a probability of saying that we have fuel. If we don't have battery and we don't have fuel, is actually 10%. And now we can compute the probability of the gauge being 0 in this each of these situations because it's 1 minus the other. And now we have some prior probabilities. The prior probability says how often we go with the car out and we have battery or fuel. Again, we are not very good. In 90% of the times we have battery, and also in 90% of the times we have fuel. So we are pretty bad. In 10% of the times we don't have battery and we don't have fuel. Cool. And now the question would be, we go and enter the car without looking at the gauge, which is the probability of not having fuel, of the fuel tank being empty. So we don't do anything. So we go to the car and we say, which are my chances of not having fuel? Actually, the chances are the chances given by the prior. No, 10% of the times I don't have any fuel, so my probability of going to the car and not having fuel is 1 in 10. So I'm not very careful about the car. And now I enter the car and I see that actually we are given, I'm reading this indicator, so I know it, now I'm conditioning on it, and it says, oh, I don't have any fuel. So now I want to compute which is the probability, the posterior probability now, of not having any fuel, given that I have just learned the fact that the indicator, the gauge fuel indicator says that I don't have any fuel. And we can just compute it. So we can compute it using probability properties, Bayes rule and sum and product rule. And we're going to get to the fact that it's 25%. Okay, of course it increases. So it's not a very good gauge. We go to the car, the indicator says we don't have any fuel. Now 25% we actually don't have any fuel. And so it increased. Usually it increases a lot. Like if the indicator says we don't have any fuel, the probability increases a lot, but this is an example for a book. And now what we want to show, we go to the battery and we want to look at the battery. We don't go to the fuel tank, we go to the battery, and we see that actually the battery is dead. And this is why the gauge, the fuel gauge says that the fuel is empty. And now we'd like to compute, which is again the posterior probability, but now we know two things from this Bayesian network. We know that the gauge says we don't have any fuel, but we also know, so here we know that the gauge says 0, but we also know that the battery is 0. We have just found out the battery is dead. So what happens, again, we are computing using product rule and Bayes rule. And actually we get to 11%. So you see what happens right now, this inference pass is open because the V structure, this node is observed. And therefore, after finding out that the battery is dead, the probability fades away. This is called explaining away or fading away. The probability of not having fuel now, it's 11%. So probably I might have fuel. Yeah, it's close to the prior of not having fuel. Cool. So this is how a V structure works. So this explains what it means for this path, this inference path, to become unblocked. It's unblocked means that this probability changes. So after I know that, the better is that the probability of not having fuel changes. It goes down from 25% to 11%. Cool, and these are like the conclusions. We have already talked about them. Another simple example from Wikipedia is like, this is another classical example. The grass is wet if the sprinkler is on or if it's raining. And we can again model it with using a Bayesian network. In this situation, it's more clear, like if it's raining, the probability the probability, sorry. So if it's raining and the sprinkler is on, the probability of the grass being wet is 99%. And again, if it's raining and the sprinkler is off, it's 80% because maybe it's not raining a lot and so on. And now the question would be, which is the probability that it is raining given the grass is wet? So we go outside, we look, and we see that the grass is wet, and we like to compute the probability that it is raining. So it's a similar way. So we can compute it. It's 35%. You can do it at home. So it's a pretty big, good chance for the exam to have some Bayesian networks and to compute the posterior probabilities after you observe where you are given some of the nodes. So it's a good idea to work at home these exercises before the exam at least once more. And now we say this separation, it's actually how we apply conditional independence for Bayesian network. So Bayesian network doesn't only have 3 nodes, it has a large number of nodes. And now let's say that we have subsets of non-overlapping nodes, A, B, and C. And we say that a path from set A of nodes to set B of nodes is blocked if it contains nodes which are head to tail or tail to tail, so the first 2 types, and the nodes are in C, like they are given, like C will contain nodes that are given or observed if you want. And if we have a V structure, so if a node in C is a V structure, is head-to-head, then neither Z node or any of the descendants should be observed, should be in C. And now, if all the paths that we have from any node in A to any node in B are blocked, we say that set A is separated from set B by set C. And you see, we write it like this. A is independent of B, and these are sets of nodes given C. And just as a simple example, again, this could be an exercise from the exam. If we have this simple Bayesian network, we are given C, so we observe C, and now we want to find out if A is set A, node A is independent of node B, given C. And we only have one path, so this is a simple example. We only have one path, but usually have several. And the answer is no, because this is a V structure, and the descendant C of E is observed. Therefore, this path is unblocked. Again, this is a tail-to-tail node, is not blocked. It's not given. Therefore, so this path is unblocked in both nodes. Now, if we are given F, this inference path is blocked, and A is independent of B given F. And one question would be, is A independent of B given nothing? What do you say? If we are not given anything, is A independent of B?
Yes, because we have a V structure with unobserved.
Yes, so they are independent because we have this V structure, and neither the node or any of its descendants are observed. Therefore, this path will be blocked here in the V structure. Yes, very good. And now some remarks on this separation. So we have seen that we have hyperparameters, for example, for the regressor Bayesian network. So hyperparameters actually they always act. So they don't have. They always behave as observed nodes. Yeah. So actually, they are always observed nodes, and more. They are always tail-to-tail nodes. Yeah. So if alpha influences anything else, this is also a tail-to-tail node. And if they act as being observed, actually they don't matter, because if they are tail-to-tail and they are observed, this path of inference will be blocked. Yeah. So these nodes are always tail-to-tail, and they act as being observed, like as being given. Therefore they have no role in this separation. And now some closing remarks after learning all these things. So in practice, like if we have ID data, so we have n samples given from the same distribution, and mu are the parameters of the distribution. So if we don't know the parameters, of course, so if we don't know these parameters, so if we are only observing these parameters, so in IID data, actually, we are given these parameters and we want to observe mu. So if we don't know mu, you see these inference passes are always open. But actually, what happens after, if we know mu, so what happens in our case is we are given mu. So we have the probability of x1 and xn given mu, given the parameters of the model. If we are given mu, this node becomes observed. It's a tail-to-tail node. Therefore, the x1 to xn become independent. So this is what happens with IID data. So once we compute the parameters of the model, or if we condition, even if we don't compute, if we condition on the parameters of the model, actually this data set will become independent and sampled from the same distribution, because each of these paths becomes blocked. So in IID, if we are given mu, the probability of the training set given mu will become independent. So this is what we actually do when we compute maximum likelihood. We are conditioning on mu, and if we are conditioning on mu, we see that they become independent. Cool. And as another example for this separation, imagine what happens for the Bayesian for the Bayesian regressor model that we have seen at the beginning of the class. So if we are conditioning on the polynomial coefficients, so if we are given, this is what means, if we have computed, if we are given the polynomial coefficients, now what happens, the new target that we want to predict becomes independent of the training set. And actually, this is a pretty nice observation, because this is what we actually do in practice. In practice, we train a model, then we can discard the training set. So we can get rid of the training set. Yeah, this doesn't matter, because if we are given mu, like if we are given W, sorry, so if we have computed W, we can forget about the training set. All the information is actually in W. So this is what it means that the training set is independent on any target, only if we are given the weights. And now at the end, actually what happens with Bayesian networks? Bayesian networks actually, or these directed graphs and directed acyclic graphs, act as distribution filters. So we might have here very complex distributions, but only some of them are passed through a given Bayesian network. For example, if the Bayesian network looks like this, without any edges, only independent distributions will pass. If we add some edges, even more independent distributions will pass, but even some other distributions. So the more we add edges, the more distributions we pass. If we observe variables, again, things change. And if we would have like a fully connected DAG, any probability distribution will pass. So you see, actually, a Bayesian network acts as a distribution filter. Not all distributions will pass, but the more complex the DAG, the Bayesian network, more and more distribution would pass. And we want to find these intermediate Bayesian networks that are complex enough to pass enough or complex enough distributions, but which are still tractable in order to compute as few parameters as possible. And the last thing we discussed is called the Markov blanket. Do you know what the Markov blanket is? From KRR? The Markov blanket is a set of nodes in a Bayesian network, which is a minimum set of nodes, in order to be correct, such that if they are given, if they are observed, xi will become independent from the entire DAG, from the entire graph. So it's a minimum set of nodes such that xi will become independent from all the graph if we are given this set of nodes. So if we are given this Markov blanket, it will become independent from all the other nodes. And let's see which are these nodes. First of all, we need to have all the parents. We need to have all the parents because if we have all the parents, if we have a path like this, or even a path like this, a path going like this, these two paths will become blocked because this will be a head to tail, this will be a tail to tail. Yeah, these two types of paths will become blocked. Yeah, and xi won't influence these nodes. Now we need to have this node observed. If this node is observed, what happens with the inference path going like this? This is again a head to tail node. So if this node is observed, this path like this from xi to this node will become blocked. But what happens if this node is observed? Now it's a problem. This inference path becomes open. So this inference path going through this V structure becomes open. And because it becomes open, now we need to also block these nodes. Like if you want, I don't know how to call them. They are not siblings. Yeah, nodes. I would say spouse if you want. For which they are also parents of the same children if you want. So you need to observe the parents, you need to observe the children, and you also need to observe this type of nodes which are also parents to the same children. If we are observing all these three types of nodes, parents, children, and parents of our children, then this is called the Markov blanket, and xi becomes disconnected, like it doesn't influence any other node in the DAG. Cool, this has been the class. Next week, you continue with Markov random fields, undirected probabilistic models. Thank you, and see you next week. Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye-bye.